first of all, I'd like to really thank Ron, Sid, and Peter, and the Simons Foundation for organizing this fantastic workshop. I've really enjoyed it a lot. So I'm also excited that there is a workshop on a subject that's very dear to my heart, which is nonlinear spectroscopy. And I'll be telling you today about a journey from a nonlinear phenomenon to a nonlinear spectroscopy. I'll be talking about going from high-order sideband generation to Bloch-wave interferometry. So as condensed matter physicists, one of the great simplifications of condensed matter physics is the notion of a quasi-particle. And of course, quasi-particles range from those in weakly correlated materials like electrons and holes in semiconductors to strongly correlated materials like holons and doublons in Mott insulators. And what an effective Hamiltonian and the notion of a quasi-particle does for us is it lets us, of course, replace a microscopic Hamiltonian for the order of 10 to the 23 particles with known interactions with a much more simple, effective one-body Hamiltonian, or maybe two-body Hamiltonian with a few parameters. And by solving density matrix equations for effective Hamiltonian, we're able to describe the quasi-particle dynamics. So it's natural, I think, to want to reconstruct the effective Hamiltonians for low-energy quasi-particles. And general framework for doing this is that we'd have some hypothesis for what the effective Hamiltonian is. We do some experiment that's sensitive to the parameters of the Hamiltonian, the band index, and the quasi-momentum, and compare experiment and theory. And ARPIS is one of the go-to methods for doing this. It's an extremely powerful method, especially for metals and 2D materials. But it does have challenges with bulk insulators and with strongly correlated materials, and it's not, it's difficult to extract wave functions directly from ARPIS. So the method that I'm going to be discussing today is high-order sideband generation. And in the basic high-order sideband generation experiment, we have a weak near-infrared field, near-infrared laser that's close to the band gap of an insulator. At the same time, we shine a strong terahertz field. The transmitted radiation, in addition to the near-infrared and the terahertz field, contains a large number of sidebands. And these sidebands are shown schematically down here. And these sidebands are decorating the near-infrared laser frequency. They're separated from one another by twice the terahertz frequency. And each sideband, of course, can be characterized by an electric field associated with the light in the sideband. And of course, the near-infrared laser can also be characterized with an electric field associated with the near-infrared laser. Now, we're going to work in the limit of linear response in terms of the near-infrared. So linear response of a periodically driven system where the periodic driving is strong. And in that limit, we'll be able to relate the electric field of a sideband, including its polarization, to the electric field of the near IR by what we call a dynamical Jones matrix. And we can measure this, reconstruct this from experiment. We can also, and it can also, in principle, be calculated from Hamiltonian. So we can close the loop in this case. Now, higher sideband generation in a two-band semiconductor can be described by this three-step model. So the first step is that an electron-hole pair is created by the weak near-infrared laser. The second step is that the terahertz accelerates the electron and hole. And in real space, the electron and the hole recombine. And when they recombine, they emit a photon, and their excess kinetic energy is carried on as the offset between the near-infrared frequency and the sideband energy. And both of these fields, you should think of them as quasi-CW. So there's no It's not pump probe in the usual sense where we have a delay between the two fields. They're both on continuously. So these are the energy scales that we're working with now. So the band gap is about 1.5 eV. There's a detuning delta from the band gap. That's the laser is detuned by delta from the band gap. This is the frequency of the energy of the high order sideband photons. And important point is that our laser fields are not so strong that they create electron hole pairs by themselves. So the motion inside the band is adiabatic. So here is a high order sideband spectrum. This is from a gallium arsenide quantum well. And the lines are spaced, sidebands are spaced by twice the terahertz frequency. And the kinetic energy associated with this sideband corresponds to having explored about 10% of the Brillouin zone in this material. Now, one of the things that's wonderful about nonlinear spectroscopies in general is that, yes, so, of course.
What makes the sidebands discrete? It's, you know, the picture you gave earlier sort of allowed, seemed like you just basically emit any amount of kinetic energy above the.
Yes, no, thank you. So at the most basic level, if I clap my hands once, I get a broad spectrum. If I clap my hands repeatedly and with the claps are exactly the same and exactly periodic, then I get a discrete spectrum. There's a more.
You mean because the terahertz is.
The terahertz is periodic. It's periodic. So we're getting a recollision twice per cycle, because, and the reason that it's 2 f terahertz instead of 1 is because gallium arsenide is symmetric in this configuration.
Sure. Yes. Your horizontal axis is wavelength. I would have thought it would have been frequency and therefore wave vector. Horizontal axis, I don't know.
Is wavelength down here and photon energy up here?
Are they equally spaced on that?
They're equally spaced in energy. Not in wavelengths. Yeah. Yes.
The way to think about terahertz is that it's only moving electrons within one band. I can neglect tunneling between the bands. I can neglect multi-photon transitions.
Yes. This terahertz is strong enough to move the electrons and holes significantly before they scatter, but not so strong that it creates tunneling between the bands, right? So this is in contrast to, say, high harmonic generation experiments.
And multi-photon transitions are also suppressed.
Multi-photon transitions are suppressed, yes. If we don't turn on the near-infrared radiation, we don't see anything. Does that answer your question? Yeah.
Why wouldn't you see something if you're at finite temperature? There are going to be some. Because I guess you need the.
It's a fully coherent process. It's a parametric process that starts in the ground state and ends in the ground state.
If you can talk about it, just
no,
wait. But the idea is that if that's near infrared, sort of a reference point, if I go a certain distance away in the energy axis, is that like mapping out the band structure, that energy away, or?
So we'll go into how we relate this, but each sideband is going to tell us a story about the band that it explored, the part of the band structure that it explored.
Since the sidebands actually cover a very large range, so do you see the effects of higher order subbands?
Yeah, in some, I think we have in some cases. It's been a long time since we did that experiment because at some point we decided that quantum wells were a little too complicated. Yeah, other question. Yeah, so we have a wealth of data that we can generate to constrain parameters. So each of these each of these matrices depends on the terahertz frequency, field frequency. And we can vary, for one sample, the strength of the terahertz, the polarization of the terahertz, the frequency of the terahertz, and of course, the frequency of the near IR. So for a given sample, we have the near infrared and the sidebands, and here schematically, we're varying the frequency, the strength of the terahertz or the polarization as we go down. So I'll say a brief word about the source of electromagnetic radiation that makes these experiments possible. And this is the free electron lasers at UC Santa Barbara. And these free electron lasers have are driven by an electrostatic accelerator that can be tuned between 2 and 6 megavolts. And an electron beam is accelerated, goes through an undulator where it gets wiggles by alternating polarity magnets and is actually collected and recirculated. So there's about roughly a few megawatts in the electron beam, and during the pulse, a small fraction of that is extracted. So the light builds up inside of this cavity that's made by 2 mirrors, and a small fraction of that is extracted. We end up with pulses that are rather long, quasi-CW, so a few microseconds long, and with frequencies tunable from 0.2 to 0.7 terahertz and 1 to 4.5 terahertz. With powers up to 130 kilowatts if we dump the cavity, which gives us a 40 nanosecond pulse and a nice quality mode. And if we seed the cavity with a much weaker, precisely tuned terahertz source, then the output can be all in a single mode. So this is very narrow band emission. Under typical circumstances, about 0.1% is the bandwidth. So in our facility, this is a diagram of our facility. So here's the free electron laser. This is the lab where we do the experiments that I'll be telling you about today. We also are doing, so these experiments use the strong electric field of the terahertz, but we're also doing some experiments using the magnetic field. We're doing terahertz electron spin resonance, and we have a collaboration with Peter looking for spin-on echoes in a different sort of time range than can be done with the 2D spectroscopy. So it's a complementary tool, and I may say something briefly about that. We can, in response to Steve's note this morning, we do a form of phase cycling in this, which I'm happy to explain, but that's not part of the main story I want to tell today. So the most recent heroes for this work are Seamus O'Hara, who's currently with the Liang Wu group. Seamus and Joe worked together very closely on all of the experiments. And Dr. Qile Wu, we've been collaborating for a number of years, and I can't really say enough about how important he has been to these experiments. So I'm going to first give you some background on high harmonic and high order sideband generation. Then I will tell you about how we can interpret the emission from high order sidebands from gallium arsenide as a Bloch-wave, a Michelson interferometer for Bloch waves. This opens the door for us to test to test an effective Hamiltonian, and then I'll talk about outlook. So high harmonic generation was first, of course, the Nobel Prize was awarded this year for high harmonic generation in atoms. I was thrilled about that. That was in 1988 that the first observation was made. High harmonic generation in solids was reported in this impressive paper from David Rees's group, and you should also see earlier work by Kono. And here they're looking at zinc oxide. There's a single laser pulse, and they're seeing harmonics up to the 25th order. So this is a very important method. And at this point, there are many, many high harmonic generations in solids. Typically, they're using sort of megavolts per centimeter lasers at tens of terahertz. It's important technologically for EUV generation. The point I'd like to make here is that for these, the laser is strong enough to create quasi-particles by ionizing or tunneling across the gap. And so the quasi-particle density is constantly increasing while the laser is on. And if you leave it on too long, the sample will ablate. So this is necessarily a transient method. And the tunneling and the acceleration are done by the same laser field. Okay, yeah. So high order sideband generation was predicted in 2007 by Renbao Liu and Fangfen Zhu, and I learned about it when I was visiting Hong Kong for a conference. He told me about this paper, and this looked like something we could do. So I immediately, when I came back, I talked to my student Ben Zaks, and we agreed he would drop what he was doing. We took a sample that we already had from other experiments. And in a relatively short amount of time, we had observed high order sideband generation from an indium gallium arsenide quantum well. So here is the near infrared, and here are the sidebands. Now, high order sideband generation can also be done with ultrafast lasers. And so here is an example from Rupert Huber's group. This is in bulk tungsten diselenide with 23 terahertz and 17 megavolts per centimeter. And so you can see a large number of sidebands. They're not as well resolved simply because the bandwidth is much broader for these laser pulses. So one of the things we did to test whether this was a really high order sideband generation is we varied the polarization of the terahertz field with respect to the near infrared field. And so we found that when it's circularly polarized, the sideband for the second, fourth, and sixth order, the intensity went to 0, which is what's expected because the electrons are sort of going, and holes are going around each other instead of running back and forth on a line. But what surprised us was that the sidebands were different intensities for near IR polarization, parallel or perpendicular to the near infrared radiation. And in that very simple picture of recollision, it's not obvious why it should matter whether the NIR is polarized parallel or perpendicular to the near IR. So this is Hunter Banks, who rebuilt the setup, wondering how high we can go and why does the near IR polarization matter. And this is Darren, who took over the experiment after Darren left. And so Hunter was able to see sidebands all the way up to the 90th order in this experiment. And so now we started to think, okay, we can maybe start turning this into a spectroscopy. And so let's think about a little bit about what story each sideband is telling us. So let's say we want to know the story that, say, the 86th order sideband is telling us. And then what story these other lower order sidebands are telling us. So the terahertz field is on. So this is just one cycle or a fraction of a cycle of the terahertz field. So this is the terahertz field as a function of time. And so for this sideband, that corresponds to an electron hole pair that was injected at this time, accelerated, and then was driven back towards the hole and recollided at this time. And you notice that this is just a classical Newton's law calculation. And you notice that the speed here is highest right before the recollision. The other lower order sidebands were injected later and recollide earlier and gain less kinetic energy. And notice that during the relevant part, during the part that's associated with the sidebands that we can observe, this is approximately linear. So for those of you who know a little bit about higher harmonic generation, there's a plateau with a cutoff frequency. For us, that cutoff frequency would be way, way beyond what we can measure. The ponderomotive energy is enormous here. And scattering is preventing those sort of longer trajectories from contributing. Now, what about scattering? So gallium arsenide has a polar optical phonon that is quite strong, and it scatters in about 100 femtoseconds. An electron with kinetic energy greater than optical phonon scatters in about 100 femtoseconds, which is less than 1/10 of our period. But the reason that we can see high order sidebands, even though there's such a rapid scattering rate, is because if it helps to look at the kinetic energy of the electron hole pair as a function of time. You can see that it's not spending very much time above the LO phonon energy. So this corresponds to a calculation for the 40th order sideband, and it's only spending about 30 femtoseconds above the LO phonon energy, which isn't really enough time for it to scatter. And so we see this sort of robust dependence, that the dependence of the sideband spectrum on near IR polarization is actually a robust phenomenon.
Sorry, Mark, can I ask a question?
Of course.
So the 2 slides ago, you said the harmonic number 35 tells me about a specific instant in time in which the electron recollides with the hole. And this is a short instant in time, but of course, the sideband is narrow because I'm repeating this many times. And so this event that is happening many times kind of narrows down in frequency, despite the fact that it carries information about something that happened in a very short.
Yes. Yeah.
Is this true? I mean, is this?
Yeah, that's the way we think about it.
But how can it be? I mean, I have a harmonic that is, let's say that I do the experiment infinite times. The harmonic will be infinitely narrow, and yet it reports information on something that happened in 1 femtosecond. How do I make sense of this?
It's happening periodically.
That's right.
And so the other contributions that happen nearby are just
interfering to make this narrow and narrower.
Yeah.
Okay. So there's some sort of diffraction grading.
So the way the experiment is done is your near IR doesn't create real particle hole pairs. They create them virtually. You're just under the gap. Is that right?
We try to go right to the gap.
Right, because what I was wondering is that exponential profile, is that some kind of a WKB sort of a X?
No.
What is the exponential telling you? Like what is
It's
that?
telling us. It's telling us what fraction of the electron hole pairs survive to recollide.
Why should it be exponential?
There's no. There's.
I mean, in the ideal case, like suppose I do a calculation with no relaxation mechanisms.
With no relaxation mechanisms, it would be a plateau.
Got it. Thank you.
Oh, okay.
Okay. I thought it was an intrinsic kind of like.
No. With the no relaxation, it would just be a plateau.
The photon does not lead to a feature either.
Yes, and that we do not understand actually. It's a surprising thing, but the yellow phonon does not lead to a sudden feature. So somehow, perhaps the dissipation mechanism is also getting altered.
That the interaction is very short, that it's not an incoherent transfer process.
Yeah, that's we don't understand that. this point. And I think it's interesting.
Couldn't it just be that the scattering of impurities is much stronger than the scattering of yellow phonon?
I doubt it in the sense that, I mean, what I remember is that in gallium arsenide, this is the showstopper, the yellow phonon scattering. But
Yeah, no, we were honestly surprised. I mean, initially we didn't see sidebands above the yellow phonon energy, and then we did, and we wondered why. Okay, so I guess I'm going to have to speed up a little bit, but I did want to give you an introduction to the phenomenon. Okay, so let's see if we can dig in and actually get some information out of about the material from this. So let's go back and think a little bit about interferometry with light. So the most common familiar kind of interferometer is a Michelson interferometer. And in a Michelson interferometer, we're extracting information about the electric field, which we can write in this way, where this phase is k dot x minus omega t, and this k and omega are related by the dispersion relation. And so if we move one mirror of the Michelson interferometer, we get an interferogram, and that can tell us the index of refraction. And if we have some smoke in our interferometer that causes dephasing, then those fringes will decay. Now, we know that in a solid, we can describe wave functions as by Bloch eigenstates of the Schrödinger equation with periodic potential. Bloch told us how to do this. There's a periodic function times this e to the I times a phase, and this phase is also a k dot x term, like the light phase. And then this term, of course, has the eigenvalues, which are the band structure. So this is our dynamical phase. And now we're going to move from quantum wells to bulk gallium arsenide because it's a simpler model. And in particular, we're going to be staying very close to the band edge. So we only have to worry about these two bands, the heavy hole and the light hole, that are right close to the band edge. Now, this is described by a very old model. It's the Luttinger model. It's not the one we heard about this morning. It's the one that he did with Walter Kohn. And there are three parameters in the Luttinger model. And so now we need to think about how does high order sideband generation work with three bands rather than two. And so here we have the near infrared radiation that comes in, creates electron hole pair, but it creates electron in two kinds of holes, heavy and light holes. They're both accelerated at the same time. They both recollide and emit. And what comes out in general is going to be elliptically polarized, and that's because the heavy and light holes have angular momenta 1/2 and 3/2. So we completely analyze the polarization of light, and we do this by Stokes polarimetry, where you send the light through a polarizer in a rotating quarter wave plate. You record the intensity as a function of the quarter wave plate angle. And so this is an example of one sideband, what we call a polarigram. And this can be basically Fourier transformed to give what are called the Stokes parameters. S0 is the total intensity, and then there are three other Stokes parameters. And together they completely characterize the polarization of the light beam. Now, those aren't so intuitive, but we can go from those Stokes parameters to sideband polarization if we express the sideband photon as in the basis of circularly polarized left and right states. Then there's going to be an amplitude, a relative phase, and an amplitude for each of these. And there's this phi is the inverse tangent of the ratio of two of these Stokes parameters, and this L squared is 1 minus S3 over 2. And so from that, we're able to extract, so this is for right circularly polarized light in, we see that the helicity of the light, the component that's in the right circular polarization is decreasing with increasing sideband order. And the opposite is true for left circularly polarized in. So I'm going to argue that this is sort of half of a fringe of an interferogram. Let's continue with this. So let's look at this a little bit more closely. So here we're going to decrease the terahertz field strength. And we see that as we decrease the terahertz field strength, the curvature of this interferogram actually increases. And so one might wonder why those interferograms change faster with order for lower terahertz field strengths. Okay, so now we're going to discuss a matrix representation of this Bloch-wave interferometer. So this is the near-infrared electric field. And then gallium arsenide essentially converts the near-infrared electric field to an electron hole pair or superposition of electron hole pairs. Then the business end of the interferometer, the two arms, we think of one of these as electron heavy hole and one of these as the electron light hole arm. And these quantities are propagators. This is when the electron heavy hole and electron light hole come back to the gallium arsenide, then they recombine and emit a sideband, which will in general be elliptically polarized. Now so I told you about this dynamical Jones matrix, which relates the sideband polarization to the near infrared polarization. And so this is general should be general for any material. For gallium arsenide, this reduces to this matrix for this product of matrices where these are propagators. And there's a lot of information in these propagators. So here, this is indexes for heavy hole or light hole. This is for sideband order. So there's a dynamical phase, there's the frequency, there's a dephasing, and there's a detuning. And these times, these are the recollision times, which are slightly different for the electron heavy hole and the electron light hole, because it takes them different amounts of time to acquire the same kinetic energy to contribute to the same sideband. And this dynamical phase is nothing but the integral of the difference in the kinetic energy between electron and hole. Now, to go a little bit further, we make an approximation that the terahertz field is linear in time, because in order to get analytical expression. And in that case, we can actually write this phase, which is the sum of this and this, as analytically, and it turns out it's proportional to the sideband order of the fifth, omega to the third, and 1 over f squared. And then there's information about the Hamiltonian in here. Okay, so here is a fit where we've adjusted only one parameter. So we're using the values of the, sorry about that. Any questions while my computer is waking back up?
This might be a good time to ask questions about the talk so far.
Actually, I missed you there. So you exactly circularly polarize, and the heavy and light hole components require different phases, but it's a diagonal matrix. So why does that rotate the polarization?
Because it's a diagonal matrix, but then they're the two dipole vectors that you have to multiply by. Oh, I'm very sorry about this. Why is it? Here we go. Okay. So we can excite with lots of different polarizations, and we get for each polarization a different looking interferogram. And for all of these, we only adjusted one parameter to fit. Now, because we have this relation n to the fifth over f squared, we should be able to scale these interferograms so that they lie on top of each other. And so when we scale the sideband order, move from n to n prime, they do nicely lie on top of each other. And that works reasonably well for all the different polarizations. So I hope I've convinced you is that what we have is a Michelson interferometer for Bloch waves in gallium arsenide. Now, and we also can analytically describe this strongly driven quantum system. So we're in a position now to test the hypothesis that the Luttinger model describes our gallium arsenide sample. So the Luttinger Hamiltonian for the heavy and light holes in gallium arsenide for Kz equals 0 can be written in this compact form where tau 0 is the identity, and these are the Pauli matrices. And here's gamma 1 and gamma 2, and then this is a vector that depends on theta, which is the angle with respect to the polarization. So what Chile did, he predicted some relations for the Luttinger model for Kz equals 0, that these diagonal matrix elements ratio should be 1, and the off-diagonal elements should have this form, which depends only on this one parameter, the ratio of 2 Luttinger parameters. So two interesting predictions. First, these ratios should be independent of n, and for all the different, and then they should have the values that are determined by this angle theta. So let's see how that works. So here is the prediction for the preferred values in the theory, and this is a reasonable agreement. Both the data are constant and close to this preferred value. Here's another angle that looks also quite good, but not quite as good. This one is looking a little bit worse, still constant, but off by a little bit. And here are all the angles. And so they're all pretty constant. They're not far from the predictions, but they don't agree certainly perfectly with the Luttinger model. And by averaging these, we can get a ratio which has somewhat large error bars. But the situation about, I don't think many in this audience would be interested in details about Luttinger parameters, but let's just say that they haven't been measured experimentally for like 50 years. And they are important for some things. So we were able to reconstruct the Bloch-wave function. I won't go into the details of this because I'm running out of time. So the data are inconsistent in detail with the Luttinger Hamiltonian. I mean, we're putting a strong requirement. We have 90 separate data points, and we're only using one parameter to fit them. So that's an example of the sort of power that we have potentially using this method. So every gallium arsenide spectrum that I could find going back 50 years has a splitting between the light hole and heavy hole exciton because there's a little bit of strain in the sample. And that's not that easy to control. And that strain splits the degeneracy at the origin, which gives rise to changes in the band structure, including Berry curvature, which give rise to effects that are not captured by the Luttinger Hamiltonian. So my final point here, okay, so we've demonstrated Bloch interferometry. We have an analytical description of this system. We've reconstructed the wave functions of holes, and it's exquisitely sensitive to the Hamiltonian. And what I'd really be interested in, and especially from this community, is for your thoughts about the possibility of extending this to strongly correlated insulators. Coulomb interactions will be shorter, dephasing rates will be stronger, dephasing rates will be shorter, and I hope that also other people will join in the fun. So thank you.
Or one or two questions. Yeah.
It's a bad fact about many strongly correlated materials that there is a fair amount of disorder in them. So that, for example, band gaps are never particularly sharp in correlated insulators. How bad is that for this?
I guess the short answer is that I don't really know. We chose to excite right at the band gap because it makes the analysis a lot easier.
I'm just saying, if you just look at the absorption, you always see a broad foot that's associated with some kind of Burbach tail or something, even Mott gaps. So, all right.
I mean, on the same, oh, I'm sorry. On the same note, I mean, do I understand correctly that to have all these sidebands, the electron needs to remain coherent over the many, many, many cycles? So
no, it needs to remain coherent over a fraction of a cycle. It remains coherent for 100 femtoseconds.
But if the electron, so that means that at the cycle that comes later, it will be a different electron.
Yes.
But will that interfere in the right way? If you take electron 1, electron 2, electron 3, electron 4 at every cycle, will I still get the constructive and destructive interference that gives me the harmonics?
We think that that's what's happening now.
So these are different electrons with different phases.
Yes.
And the only important thing is the optical phase, which is given by,
yes.
I see.
This exact picture for atoms too.
That's right. That's exactly true. These are even different atoms. All right, fine.
Last question, Eugene, and then we can have the next speaker set up meanwhile.
Is it clear that you can treat electrons and holes as completely non-interacting? Because I can imagine, like, once electron and hole recombine, this energy is not emitted, but goes into another hole electron pair resonantly. And so that would actually contradict this simple non-interacting model.
So in gallium arsenide, the exciton binding energy is 4 millielectron volts. And the fields are so strong that if you did sort of that the exciton would be ionized for sort of most of the time. I mean, the exciton would exist if you imagine a quasi-statically varying the electric field between 0 and 70 kilovolts per centimeter. The exciton would only exist for.
But I'm not thinking about exciton. Electron hole pair.
Yeah.
When it combines, it can give energy to create another electron hole pair, right? Those they being an exciton. It's just like in superconductors, it's a known problem. If you ask how long does it take for quasi-particles to relax by emission into a phonon, it's actually much longer than a simple Fermi's golden rule, because it turns out like when you recombine a quasi-particle, you generate a phonon, but then this phonon generates another quasi-particle.
Yeah, no, but this is a coherent recombination process
that would still be coherent, right? Because
well, it's coherently going back into the near IR, right?
Exactly.
So it's that closed cycle.
You're talking about an Auger process here, or is that what it is?
no, I'm not
Where you
sure.
kind of, and kill an
Some of the electron hole
up
pairs don't recombine, they just scatter and then they get heated up.
I guess my concern is just completely neglecting electron-hole interactions. And I can see how they can give rise to something which is at least partially coherent through this correlated annihilation and creation process.